All right, we're ready for our first set of statistical tests or group of tests, and these are going to be collectively known as t-tests. As you note there on the screen, there are three different types of t-tests: the single sample, the independent sample, and the dependent t-test, which is also sometimes referred to as matched pairs. Again, part of the challenge for statistics is language and knowing what people mean, and you'll see this written various ways, so dependent or matched pairs. One of the things that I do want you to note about t-test as a whole, we will use t-test whenever you want to compare two groups or two means of two groups. Okay, so if you have two groups, just automatically know we're going to be testing using t-tests. The other thing that I want you to be aware of is that the distribution for the t-tests are roughly normal, so it looks, like a normal curve, just like any other curve we've looked at up to this point, with one small caveat. If our sample sizes are small, then the actual distribution for the t-test is a little platykurtic. But as our sample size increases, so too does our curve more likely resemble the normal curve. Okay. So with that in mind, we're going to jump into the single sample t-test and go through an example. For the single sample t-test, we are going to use, again, as with all t-tests, when we have two groups that we want to compare, but we can use the single sample t-test in a similar way to what we did with the z-score. When we want to compare a single sample, hence the name, to a known population mean. So in the case of our long-term alcoholics, we could have also run that data using a single sample t. But we can also look at the example here on our screen as another illustration of a single sample t-test. So imagine we have some nurses in the room, which I believe we do in both of our classes. Likely up to this point, we've had at least some nurses. So imagine our nurses have discovered some new illness, and they want to be able to determine if one of the symptoms related to this illness is increased body temperature. So in order to test this little theory that they have, the nurses recruit 11 individuals who have been identified or diagnosed with this new illness, and they record their body temperatures. The data that I've listed here just made up, but let's say it represents the data of these 11 individuals. The question we want to know is, does the illness appear to increase body temperature? Some of you may be looking at these values and thinking, it doesn't really look like it. But maybe. Okay, so we don't know, and that's the reason we need to run an inferential test to see if there is some kind of statistically significant difference in the body temperature of those who are sick versus not. So if you will, go ahead and take out your NHST list, and we're going to walk through the 7 steps of NHST for this example. So first thing we want to do, write out our hypotheses. Again, we start with a null, and basically what we're saying is the body temperature for the population of ill individuals is approximately equal, to the body temperature of healthy adults. That's the null. There's no difference. They're roughly the same. Our alternative is that these sick individuals actually have a lower temperature than healthy adults. And then our other alternative, and this is what is being predicted by the nurses in our scenario, is that the body temperature for those who are ill is actually greater than the body temperature for an average healthy adult. Okay, in this case, step 2, we want to conduct a test. In this case, we're looking at the single sample t. Again, why? Because we have two means we're wanting to compare our sample to a known mean. And the known population in this case, what is our known mean? We know it is roughly 98.6. Okay, that is the average body temperature for the healthy population. We know there's some variance there, but this is the mean. So we want to test this. So the next step is then to find our critical value. As we said before, just always assume alpha is 0.05. And in this case, in order to find our t-critical, we're moving away from z-scores, we're in t-tests now, so we've got to find a t-critical. we're going to have to look at a t-distribution table. Well, as we are moving deeper into inferential statistics, there is another concept or construct that we have to be familiar with, and it's this idea of degrees of freedom, which you'll note are generally written or notated as lowercase df. So whenever you see df in the literature, they're talking about degrees of freedom. And degrees of freedom, really, if you want to think about it in the term of money, it's what allows us to be able to buy things. It gives us, in statistical terms, more power. The more degrees of freedom we have, the more power we have to sort of buy an effect or to find an effect. So we want studies with lots of degrees of freedom. Now, some of you hopefully are recalling the easiest way to increase our power is to increase our sample size. And what you'll note here is degrees of freedom are intimately tied or directly tied to sample size, which is why we want degrees of freedom to be greater to give us more power. So if you'll note here, degrees of freedom for a single sample t-test equals n minus 1, which in this case, the scenario we're using, we know that the researcher recruited 11 individuals, right? 11 individuals who were diagnosed with this illness. So if we calculate the degrees of freedom, n minus 1, we get degrees of freedom equal 10. Now, why do we need degrees of freedom moving forward? Well, one of the things that we have discovered is that in order to calculate these statistical values, we have to sort of make an adjustment to keep from overestimating our significance. It's in essence a way to control for type 1 error inflation. We adjust our degrees of freedom. And the other thing that we find, which is important with these degrees of freedom, is that our distribution changes based on the number of degrees of freedom. As I've told you, the greater the sample size, the more this t-distribution resembles a normal curve. For fewer numbers, the more platykurtic it is. So in essence, this curve changes for every degree of freedom we add. Or you could think of it this way, there are multiple distributions, so to speak, for the t-test. So in this case, we know we have 10 degrees of freedom. We've got to find the t-critical associated with 10 degrees of freedom. Okay? So if you'll look at this table, you'll notice that there are sort of two headings here, two-tailed test, one-tailed test. One-tailed test, put a little frowny face next to it if you want. This, by the way, is from the book, page 803. You'll see there is a t-distribution table, but the one-tailed test, we're not going to use them. I don't like them. There are cases where we can make a rationale for it, but we're not going to do it in this class. We're always going to go to two-tailed test. So there in that, under that two-tailed section, then you see two different alphas. We see an alpha of 0.05 and an alpha of 0.01. They're the most common alphas, which is why they're generally reported. We're always going to assume 0.05 unless otherwise stated. So for this particular example, we want to follow down to 10 degrees of freedom, two-tailed test with an alpha of 0.05. If you were to go down to the DF of 10, which is near the bottom half, I'll say, follow that over to the 0.05, and you will find that we have a t-critical of plus or minus 2.23. Okay, so our t-critical, is plus or minus, what did I say it was? Plus or minus 2.23. Okay, the reason we use the plus or minus in this case, you'll notice there are no negative values on this table. So we have to talk about plus or minus because it could be on either end of the curve, the negative side or the positive side. So our t-critical will always be positive or negative. It's a symmetrical distribution, so it's like the z, whatever we do to one side, we do to the other. In this case, they've already, in these tables, allowed for the two-tailed test, so you don't have to make any conversions. So it is a 2.23 critical value. All right, step 4. We want to actually conduct the analysis. Well, from this point on, you're going to be using SPSS. And the output that I've given you here is output from SPSS. You will become intimately familiar with this output, but we're just going to walk through some things here. This top box that you'll see, or the first box there, is what we would consider some of the descriptive statistics related to our sample. So you see temperature there, which is our variable. It's what I've called our variable in the data set. You'll see the N there of 11, which we know that's the number of our participants. You'll see the mean score there, which we know our sample mean then. Our sample mean, based on that value, is 98.318. APA suggests or asks that we round everything to 2 decimal places. So our mean for this sample is going to be 98.32. Okay, so if we round it, it's 98.32. The standard deviation for this sample then is 1.53, again rounded to 2 decimal places. And that's the important information you want to pull from that top box. The second box now is where we get into our actual values. And you'll notice in the very top heading there, you'll see a 1 sample test, and then right below that in that first box there, in the center, is a test value of 98.6. This is, in essence, the population value we want to compare it to. So what we're saying is we want to test the mean of our sample to the mean of this known value, okay, which is why we're doing a t-test. We're comparing 2 means. All right, so now let's go to the far left on this second box. Again, you see the variable name, which we've called temp, and then you see this value with a heading of t. This is our t observed. So if we were to write this out, we can say our t obs equals, in this case, what is our t obs? What is the value for t obs? It's negative 0.609. For APA, whenever you have a value that is less than 0, and it could be more than 0, in this case a t-value could be more than 0, include the 0. So instead of writing just negative 0.609, we would put t-obs equals negative 0.6 and rounded to 0.61. So in this case, our t observed is negative 0.61. We see our degrees of freedom in the next column, which is 10. It matches what we calculated for our degrees of freedom. And then you'll see this heading called significance, parentheses, two-tailed. Okay, it should be a little bit of a giveaway. It's two-tailed. SPSS labels the p-value always as sig. Okay, so when we talk about significance, that is its reference to the p-value. And when you get here face-to-face, we'll have some of these to hand out. You can make some notations here, and we'll get more familiar with all of this. But again, if you want to make a note here, whenever we talk about significance for SPSS, it is the p-value. So in this case, what is the value for our p? Okay, so if this is our t observed, what is our p observed? Our p observed equals what? It equals 0.56 rounded to 2 decimal places. Our p-value can never be more than 1. So in this case, we never include the 0. We just say p-obs equals, or more accurately, let's take the obs off of here because you'll very rarely see p-obs written. It's just going to be p equals, in this case, 0.56. Okay. So now we know what our t value is. It's 0.61. Our p value is 0.56. And we'll talk about what these other values mean here in just a moment. Okay, so we've run our analysis. Here it is. We've got our values. Step 5, we want to make our conclusion. Okay, so let's look at this very carefully. If our p is 0.56, Is that in the rejection region? Some of you may be saying, I have no clue if it's in the rejection region. How do we know? Well, again, where is the value for our rejection region? It's 0.025 on either side, which equals 0.05. So our P critical is 0.05. So if this is 0.05 or smaller, and our P is 0.56, is this P value larger than 0.05? It's way larger than 0.05. In fact, it's 0.56, which means it's probably somewhere here. Okay, this is the probability. In other words, about 56% of the time, we are likely to get this value if we just randomly sample from a healthy population. If we are likely to get this value 56% of the time, it is not in the rejection region, so we fail to reject the null. In this case, what we conclude in a write-up, and this is how you need to start wording things for APA, is something to this effect. On average, the body temperature of patients with the new illness, and then put their means and standard deviations, was not significantly higher than the average body temperature of healthy individuals. Okay? Again, you put their mean, and then we're going to put our actual statistic. And this is what APA wants. You put the type of test you ran, in this case it was a T, with 10 degrees of freedom. That's what's in that parentheses there. And then I want to actually put my T value. In this case, it's negative 0.61. And then I also want to put its related P value. And I goofed, I guess I put 0.57, but it should be 0.56. Okay, so P equals 0.56. And this is the basic write-up for SPSS. Those values that you see in this wording is what you need to include. So again, our conclusion is, on average, the body temperature of patients with new illness was not significantly higher than the average body temperature of healthy individuals. We could then go and calculate Cohen's d for this. Okay, let's go ahead and do that. We calculate Cohen's d. What we're going to find is our mean is 98.32. We are going to subtract 98.6, and we're going to divide that by our population standard deviation, which in this case we don't actually know. So we are going to use our sample standard deviation as an estimate for that. So our sample standard deviation is 1.53. I got that from the top box. So now all we have to do, if you get your calculator out, I've got mine out, you're going to take 98.32 minus 98.6, and you're going to divide that by 1.53, and I get a 0.18. Okay, and by the way, this is absolute value, so you don't have to worry about the negative. So I get a D that's equal to 0.18. Okay, 0.18, which we go back to is that small, medium, or large. Okay, it's below 0.2, so this is still a small effect. Okay, so we know this is small, but that sort of makes sense, right? Because we just concluded that we didn't find anything statistically significant. So we would imagine it would be small, though I will tell you there are times that you may find a large effect size even with a non-significant result, and it might indicate you just didn't have enough power. Your sample size wasn't large enough to detect it, but it might still be there. So we'll still calculate the effect size. And then lastly, we want to construct and interpret our confidence intervals. Well, the good thing here is SPSS prints these out for us. So if you go to that second box again, to the far right, you'll see a heading called 95% confidence interval of the difference. You have your lower and your upper. That lower is the lower bound, the upper is the upper bound. So you just write those out rounded to 2 decimal places, And basically that's the 95% confidence interval for our mean difference. Okay, now that's important to note. We're talking about the mean difference, not the mean. So we're talking about the difference between what we expected to find and what we actually found. And so the range of that difference is somewhere in the real population between negative 1.3 and positive 0.75.